Let's jump right into this explainer. Today we're exploring a fascinating process that happens literally millions of times a day, right in front of our eyes, yet we barely give it a second thought. We're going to discover exactly how computers manage to translate invisible ones and zeros into the things we can actually see, hear, and touch in the real world. Have you ever actually stopped to wonder how an invisible process buried deep inside a CPU magically becomes a vibrant movie, a printed page, or a pulsating beat? Think about it for a second. Inside your computer, everything is just math and electrical currents. There are no pictures, no words, and no sounds in there. Yet somehow that raw, unfeeling data is perfectly transformed into the vibrant, sensory-rich human experience we rely on every single day. Well, the crucial point here is that an output device is essentially the ultimate translator. It bridges the gap between a computer's electronic brain and our very human senses. It takes the raw input data that the computer has just processed and turns it into a format we can actually understand, like text, images, or audio. Because without this hardware, we literally wouldn't even know what the computer had accomplished. So here's our quick roadmap for today. We'll start with translating data for humans, move through visual output, print output, audio output, tactile output, and finally wrap up with the broad importance of these output devices. Starting off with Section 1, translating data for humans. Without these hardware translators, all the incredible processing power of a computer would just be locked away in a format we simply cannot perceive. Output devices are the tools that show us what a computer is actually doing. So whether you're crunching numbers at work, researching at school, or just gaming at home, these components take those complex electronic operations and translate them into text we can read, pictures we can look at, sounds we can listen to, and even physical objects we can hold. Moving on to Section 2, visual output. We'll be looking at monitors and projectors. Now, there has been a massive evolutionary leap in how we actually see digital data. We started with classic CRT or cathode ray tube monitors. You probably remember those. They were heavy, bulky devices that generated a beam of electrons from internal guns, literally striking millions of red, blue, and green phosphorus dots on the inner surface of the screen to generate an image. Fast forward to today, and we've transitioned to flat panel displays. These are incredibly lightweight, use way less power, and operate silently by just passing light through liquid crystals or a solution of noble gases and mercury that converts to plasma. It's a pretty incredible leap in visual translation. But what if we need to share that visual data with a massive audience? That's where projectors come in, using lenses to magnify images while taking up exactly zero floor space. The computer sends a signal to a video card, which transmits it directly to the projector. The projector then uses intense light and lenses to blow up that visual data onto a huge wall or screen. And because they can be mounted right on a ceiling completely out of the way, they remain a highly practical and cost-effective output for teaching or large group presentations. Next up, Section 3, print output. Let's talk about printers and plotters. What's really interesting here is the stark mechanical difference between older, quite violent impact printers and the sleek, silent operation of modern non-impact page printers. Impact printers, like your old dot matrix machines, literally smash a physical hammer or print head against an ink ribbon to force characters onto the paper. It is highly physical and really loud. Non-impact printers, on the other hand, which are often called page printers because they do a full page at once, produce characters and images without any striking mechanism at all. They just rely on elegant laser technology or tiny, precise sprays of inkjet droplets to seamlessly transfer the data. For massive architectural blueprints or precision vinyl signs, standard printers just won't cut it. Instead, we rely on 4 highly specialized types of plotters. First, you have a pen plotter, which physically draws lines with pens on the paper. Then there's an inkjet plotter, which sprays tiny droplets for large format photos. A cutting plotter actually swaps the ink for a sharp blade, literally slicing out designs from adhesive-backed vinyl. And finally, the electrostatic plotter uses electric charges to attract toner directly onto the material. It's a fantastic example of hardware specifically tailored to professional heavy-duty output needs. All right, Section 4, audio output, speakers and headphones. So, speakers take electronic signals from a sound card and use these vibrating internal amplifiers to recreate everything from a delicate whisper to an earth-shaking bass line. Here's how it works. Once the computer's sound card converts the digital file into an electric signal, the speaker takes over. The internal amplifiers vibrate at varying frequencies. These vibrations increase or decrease the amplitude and volume, actually pushing the air to create the exact sound waves that our human ears were designed to hear. But when we want that audio experience to be completely private, we use headphones. They convert electrical energy directly into mechanical energy right against our ears. Basically, headphones serve the exact same function as speakers, but on a much more intimate scale. And they come in a few variations to fit our lives. We have standard stereophones for private listening, highly portable earphones or earbuds that go right into the ear, and of course, headsets, which brilliantly combine the output of listening with the input of a microphone for two-way telephonic communication. Moving into our physical senses, Section 5, Tactile Output, Touch and Beyond. You might not immediately think of GPS as an output device, but it absolutely is. It brilliantly translates invisible satellite radio signals and mathematical trilateration into your exact physical location. A global positioning system collects incredibly complex variables from a network of satellites, things like exact time, spatial location, and speed. The computer analyzes all this data through a math concept called trilateration. The output? It shows you exactly where you are standing on the Earth. And incredibly, it does all this entirely independently of standard internet reception. Now, this is a deeply impactful example of tech translating digital text into physical raised dots, ensuring the digital world is fully accessible to the visually impaired. Invented way back in the 19th century by Louis Braille, the modern Braille embosser operates as a highly specialized tactile printer. So instead of ink, it employs a complex set of mechanical pins or embossing heads to punch physical, raised dots right into paper or other materials. It allows digital content to be read purely by touch. And if we want to bring entirely new ideas into the physical world instantly, 3D printers are totally revolutionizing manufacturing by literally building prototypes layer by layer. Just think about how wild this is. You start with a purely digital 3D model on your screen, and this output device literally manufactures it into a tangible, three-dimensional object you can hold. By layering material over and over again, it drastically reduces the time and cost required to turn an idea into a physical prototype. It's a real game changer in industries like automobile manufacturing. Let's pull this all together in Section 6, the importance of output devices. To summarize our journey today, these output translators do far more than just show us text on a screen. They automate factories, enable global communication, and even power entire virtual realities. It is super clear that output devices are the true communicators of the digital age. Beyond just monitors and headphones, these devices use network cards to facilitate global data transfer. They act as actuators controlling massive robotic arms in industrial automation. And they are the very foundation of virtual and augmented reality, using headsets to overlay digital information directly onto the real world around us. If we've gone from smashing ink ribbons onto paper to exploring fully immersive virtual realities, it leaves us with one really fascinating question to ponder about what the next era of computer output will look like. We currently rely on output devices to act as translators for our eyes, our ears, and our hands. But as technology accelerates, you have to wonder, what happens when the computer no longer needs a screen or a speaker? Will the ultimate output device of the future bypass our physical senses entirely and just speak directly to our brains? It's definitely something to think about. Thanks for joining me on this explainer, and keep questioning how the digital world connects to your reality.